All right, so we've done the Wilcoxon one sample or matched. This now we'll look at the two samples. So we've got two independent samples. And here they are. So here are two samples. And what we've got is we've got two groups. Let's call it the low exposure group and the high exposure group. This is all in the textbook if you want to read up about what this is all about. So what the idea is here is throw them all into the pool together, all your observations, put them all in together, and then rank them, and then collect them back. So we see that the smallest observation is this 28 here. The next smallest one is this one, 2, is this 34.5. The next smallest, 3, is the 35. Then the next smallest, well, they tied, and so they each get 4.5. So the next one down is the one with the 6, then the 7, the 8, the 9, and so on. So you've understood. Throw them all in, rank them. Then look at the total ranks in the one sample, look at the total ranks in the other sample. If the two samples are the same size, then these two should be roughly the same if the null hypothesis of no difference is correct. Right? That's exactly like we did with the t. The only difference is that with the ranks, we've got much more control about the variances. We know how to handle that and everything. But here they are. So here is the recipe. Throw them all in and then rank them. So these are the overall ranks. Then look at the sum of the ranks in one of them. Doesn't matter which one you choose, just choose one of them. And the null hypothesis is that they are two samples from the same population. So that's the null hypothesis. So you'd expect the two ranks, the two sums of the ranks be the same, if the two sample sizes are the same. If not, you'll do the appropriate weighting. All right? And so what we do, here's the formula. We can get our approximate standard normal and so on. And in this example, the p-value is 0.186. We don't reject the null hypothesis. But it's rather straightforward. But one thing I wanted to pay attention to is if we looked at the data itself without doing the ranking. So before today, before learning about this stuff, what would you do? You might do a t-test. All right, so you might summarize, here are the means for the low exposure group and the high exposure group. So there were 21 in the low exposure group, 18 in the high exposure group. The mean are 49.3, 46.2, and here are the standard deviations. They look approximately equal, maybe not, but you know, we would do the appropriate t and go ahead. Now, unfortunately though, we would say, wait a minute, if I were to do the t, I would really want approximate normality of my data. So let me look and see how approximately normal is my data. Well, if I look at the low exposure group, here it is, it does not look very normally distributed. I look at, you can see I've superimposed a normal curve there. I've superimposed a normal curve, doesn't look very normal. Even when I combine the two, they don't look too normal. So, you know, maybe we shouldn't be doing the t-test, but doesn't matter. We're halfway there, so let's do it. And now, here's the rank sum. If we did the Wilcoxon rank sum, we see that the p-value is 0.1849, whereas if we do the t-test, so if we do the t-test, the p-value is 0.198. So, point is that in this example, even though the normality assumption looks like it's quite violated, we still get roughly the same answer. So it looks like the t is a little bit more robust than we had first thought of. Okay, but be careful how you handle that stuff. You know, you got everything on the computer. Might as well do. And there's 3 ways of doing something. Do it 3 ways, and then see if you get the same answers the 3 different ways, or whether you're going to have to realize, why am I getting different answers different ways I'm doing it. All right? So finally, in summary, When should we use the Wilcoxon? When should we use student's T? Well, the advantage of the Wilcoxon is we don't need to assume anything about the parent or population distribution of the variable in question. So we do not need to assume normality. That's the advantage of the Wilcoxon. Okay, so the Wilcoxon is more robust. But you're not going to get something for nothing. So how do we pay for this? Well, here's the disadvantage. If, in fact, you were justified in making your normality assumption, so if, in fact, you could use the T, how much do you lose? And the answer is not that much. When, in fact, you have normal data, the Wilcoxon is about 95% efficient. So, you know, if you've got 20 observations, the Wilcoxon is about as efficient as if you had 19 observations and use the T appropriately. So it's up to you. It's up to you. You know, I like the Wilcoxon, and as I said, it's not that expensive. And it's a good backup to see if what I've done is, you know, is I'm getting a totally different answer than I would have had I used the T. So they're good in that respect. Okay, that's it.